Welcome to lesson 2.7, Conjectures. So the big idea for today's lesson is that in geometry and in mathematics, only proofs can establish a conjecture's truth. So in other words, we're going to start to dive a little bit deeper into the idea of conjectures, which would be an educated guess or opinion. But the main idea that we're laying a foundation for, and we'll be building off of basically the rest of the school year, is that idea that we need to use proofs to establish truth in mathematics. So again, a conjecture, we simply can define as an educated guess or opinion. So to show a conjecture is false, a single counterexample must be shown. So simply put, if you find one instance in which the conjecture is false, you can conclude that whole conjecture is false. On the flip side, to show that a conjecture is true for all cases, it must be proved. And again, we'll get into the idea of proofs in the near future. Even if the conjecture is true for every instance you have checked or tried, that still does not prove the conjecture. It simply shows the conjecture is reasonable. To be proved, it would have to be true without a doubt for every possible scenario. So you could check 1,000 instances and still not have come up with the full proof you need, because there could be an instance out there that you didn't think to check that makes it false. So to show a conjecture is false, we need one single counterexample. To show a conjecture is true, it must be proved for all cases. So looking at that idea, complete the conjecture by checking specific cases and finding a pattern. So rather than checking every scenario, a lot of the times with conjectures to see if they're reasonable or not, we look for that idea of a pattern. So the conjecture says that the product of any two odd integers is blank. So I'm just going to try a few different instances. Product meaning multiply. Two odd numbers, integers are whole numbers. So I'm just going to try multiplying some odds. 1 times 3 is 3. 3 times 5 is 15. 5 times 7 is 35. 3 times 3 is 9, 7 times 3 is 21, and so on. If I try some negatives, negative 3 times negative 5 is 15. Negative 5 times positive 7, negative 35. So what I'm seeing is a pattern that all of my final products are also odd integers. So my conjecture, based on the pattern that I'm looking at, would be that the product of any two odd integers is an odd integer. For part B, the conjecture starts with saying the average of any two consecutive even whole numbers is blank. So consecutive would be one right after the other. So we're looking at consecutive whole numbers that are even. Oops, lost my screen there, go back. So we're looking at consecutive whole numbers that are even, and the average of those, which would be dividing by 2. So in this case, consecutive evens would be like 2 and 4. So the average of them would be add them up, divide by 2, or 4 and 6, 6 and 8, 0 and 2, 24 and 26. So a few examples there. Doing the average, so add the numbers, divide by 2, and I start to see a pattern with my answers. My answers all come out to be odd numbers. So to finish that conjecture based on my pattern, I would say the average of any two consecutive even whole numbers is an odd whole number. That's what the pattern's showing me. Do I know if that's true for all cases? No. But is it looking more and more reasonable with each example? Yes. So example 2 asks us to consider the conjecture. So the conjecture we're looking at states if the product of two integers is positive, then those two integers must be positive. So an instance of the conjecture, an instance means a case where it's true. So if I take two integers, two positives multiplied together, give me a positive. So the product's a positive and both integers are positives. A counterexample to that would be a product that's positive, but then my integers not both being positive that are being multiplied. So there's many counterexamples. I chose this one. A -2 multiplied by a -3 is a +6. So in this case, my two integer multiples are negatives, proving this statement false. So to restate the conjecture so that it's true, we could restate that to say, based on the data we have, if the product of two integers is positive, then the two integers must have the same sign. So I apologize that got cut off, but it would say if the product of two integers is positive, then the two integers must have the same sign, meaning both are positive or both are negatives. And then we get into our final page here, examples 3 and 4. Example 3 says, determine whether each conjecture is true or false. If true, explain why. If false, give a single counterexample. So in A, the average of any two consecutive even numbers is an even number. So from before, up here, we knew that was false. So I just chose one of these as my counterexample. So 2 plus 4 divided by 2 equals 3. So that counterexample shows this original conjecture is false. In B, if two equilateral triangles have equal perimeters, then their sides have equal lengths. So in this case, what I start to think about is that all triangles have three sides that make up their perimeter. In equilateral triangles, those three sides all have to be the same length. That's from the definition of equilateral. So any equilateral triangle's perimeter, if we took that divided by 3, we would have the side length. So if the perimeter of triangle A was x and the perimeter of triangle B was y, if x equals y, then x divided by 3 equals y divided by 3. So that's showing mathematically that their sides have equal lengths. So if I take the perimeter, divide it by the 3 equal sides, if those perimeters are the same, then the side lengths will also be the same. In C, any four-sided polygon is a square. So obviously that's false. We have many quadrilaterals that are not squares. In this case, I drew a trapezoid. Could have drawn a parallelogram, a rhombus, a rectangle, or many more. And then in number 4, states Anissa makes the conjecture that there are no white tigers. So Anissa is saying there's no white tigers in existence. How could Anissa prove this conjecture? Anissa would have to literally find every single tiger that exists in this world or on this planet and show that each one of those is not white. Now, for John to disprove this, he has an easier job. John could prove that this is false by finding a single counterexample. So if John found a single white tiger, that would prove Anissa's conjecture false. In order for Anissa to support or prove her conjecture, she would have to identify every tiger on this planet, showing that they're not white. So the main idea, though, for this lesson and laying the foundation with conjectures being true or false goes back to this idea of if it's false, you need a single counterexample. And if it's true, it must be proved, which we'll look at how we do that using proofs in the future. And if we're just looking at patterns and many different instances, but we have not tried them all, then we are showing the conjecture is reasonable.